Let's talk about torque, and torque causes a change in rotation. We do have to kind of look and see what information we have before we decide on a path for solving torque with change in rotation problems. So if they give me torque and displacement, so if this is the case, I'm going to be going ahead and using work. And so the work is equal to the torque times that displacement if the torque is a constant. If you have a torque function that's dependent on theta, you're going to have to go ahead and integrate that function with respect to theta to find the work. Once you have that work, we can now move into the work kinetic energy theorem. On the other hand, if you're given torque and time, okay, if you're given torque and time, we can talk about a change in angular momentum is equal to torque times delta t. Again, that's if that torque is constant. Or if that torque is a variable with time, now we can talk about the change in angular momentum by integrating that torque function with respect to time. We can also, if we have a torque function with respect to time or a constant torque, we can go about using Newton's second law on rotation and get an alpha equation and then go from there into rotational motion. So these are kind of the two options we have for dealing with torque. So the first thing we want to look at is what information do we have to go with it. Okay, so let's do an example. So this one says an electric motor delivers a constant torque of 20 Newton meters as it accelerates a 3.2 kilogram uniform disc with a diameter of 0.24 meters from rest. Okay, so they're telling me it's a uniform disc. They're telling me it's a constant torque. They're telling me a diameter. We better change that to a radius. And it's starting from rest. And then they want to know what is the final angular velocity of the disc after 3 revolutions. So they tell me 3 revolutions. That's my clue that they're telling me theta. Okay, revolutions we will have to change to radians. So in order to deal with this, we are going to have to do the work kinetic energy theorem. So let's write that out real quick here. There, that was easy. The next thing we need to do is we need to cross stuff out. So our disc is not changing its height. There are no springs attached to it. It does say it starts at rest, and there is no mention of friction. So our equation drops pretty quick to now we have work is equal to our kinetic energy at the end. And since we had a constant torque, we're going to do torque times theta is equal to, and now because it's rotating when we do kinetic energy here, we're going to have a 1/2 I omega squared. And our goal is to solve for that omega. So we'll do a little algebra here. So we have 2 torque times theta, all divided by I, take the square root, and we will get our omega. So let's put in our numbers. So 2 times 20. That angle, they said it was 3 revolutions. So we just need to get rid of revolutions and go to radians. And there's 2 pi radians in 1 revolution. So we have 6 pi in there, divided by 1/2 times the mass, which was 3.2, times the radius squared, 0.12. Again, we just have to make sure they gave us the diameter, so we had to change it to radius. Take the square root and get your omega value. When I typed it in, I got 180.9 radians per second. If they ask for it in revolutions per minute, I would have to convert that back. All right, there's a practice problem next. Go ahead and try that.